11.1 is on goodness of fit. And a goodness of fit test tests the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution, where a one-way frequency table conforms to some particular distribution. And the requirements of this test: the data have been randomly selected. The sample data consists of frequency counts for each of the different categories. For each category, the expected frequency is at least 5. And the hypothesis test for this, we would take the null hypothesis of the frequency counts agree with the claimed distribution, and the alternative is that the frequency counts do not agree with the claimed distribution. The test statistics specifically is a chi-square distribution, which for this particular test would be equal to the sum of the observed frequencies minus the expected frequencies squared divided by the expected frequencies. This has k minus 1 degrees of freedom, and p-value can be computed in SAS. Goodness of fit tests are always right-tailed. O is observed frequency, E is expected frequency. If the expected frequencies are all equal, the expected frequency will be the sample size divided by the number then of actual observations, so n divided by k. If the expected frequencies are not all equal, E is equal to n times p for each individual category. So the number of observations times the probability of each one. If the observed and expected values are close, the test statistic is small and the p-value is large. If the observed and expected values are far, the test statistic is large and the p-value is small. So if the p is low, the null must go. If the p-value is small, we reject the null hypothesis. And we can see this displayed inside of this picture as graphs over here. So for example, if you want to calculate the expected counts of this particular, let's say, longer die, you get the numbers of 1, 2, 3, 4, 5, and 6. Observed frequencies are 13, 6, 12, 9, 3, and 2. If we add all these up, we get a sample size of 45. Since all these are equally likely, we have a k number of outcomes of 6. Since each of these are equally likely, the expected frequency would just be n divided by k, so 45 divided by 6. This gives us a value of about 7.5. Right. For this one down here, these numbers are 1 through 6, but this has a probability of 0.5, 0.1, 0.1, 0.1, 0.1, 0.1. Observed frequency of 13, 6, 12, 9, 3, and 2. This has a sample size here of 45, but now we have to use n times p. So to get, for an outcome of 1, this would be 45 times 0.5. This gives us a value of 22.5 for 1 here. For all the other ones, this is 45 times 0.1. This gives us a value of 4.5 for all of these other expected frequencies. Let's say, for example, a random sample of 100 weights of Californians is obtained, and the last digits of those weights are summarized in this table down here. Based on data from the California Department of Public Health, when obtaining weights of subjects, it is extremely important to actually measure their weights instead of asking them to report their weights, since they might undercount what they weigh. By analyzing the last digits of weights, researchers can verify that they were obtained through actual measurements instead of being reported. When people report weights, they tend to round down, and they often round way down. So a weight of 197 pounds might be rounded and reported to a more desirable 170 pounds. Because, that's pretty close together, right? Reported weights tend to have many last digits, consisting of 0 or 5. In contrast, if people actually weighed, The weights tend to have last digits that are uniformly distributed with 0, 1, 2, all the way up to 9, all occurring with roughly the same frequencies. Test the claim that the sample is from a population of weights in which the last digits do not occur with all the same frequency. Based on the results, can we conclude that the procedure used to obtain the weights? For this, we have a simple random sample. We can see from this table down here, this is a frequency table. And they're all equally likely, with an expected value of 100 possible observations divided by 10 choices. This gives us an expected value of 10, and that's at least 5, so that's all good. The null hypothesis is that all of these probabilities are equal. So P1 is equal to P2 equals P3 equals P4 equals P5 is equal to P6 equals P7 equals P8 is equals to P9. The alternative is that at least one of these is not equal, or at least one is different. At least one is different. Alright. And if we were to go about doing this, we would get a chi-squared value of 212.800 and a p-value less than 0.0001, which you could definitely tell because we have a critical region over here on the right. That's very low. So we're going to reject the null hypothesis. So there is sufficient evidence there's sufficient evidence to claim that the last digits do not occur with the same relative frequency. Or to put into other words, at least one of those is different. Which one? That's not what the test is based upon. It's just finding out that they're not all the same. And for my next example here, let's say according to Benford's law, which is a lovely law here, detailed up here in this data table, but a variety of different data sets include numbers with leading first digits that follow the distributions shown in the first two rows of this table up here. Data sets that tend to follow Benford's law include a class of errors in clinical trials, as well as magnitudes of gradients from magnetic resonance imaging or MRI scans, computer tomography, CT scans, and ultrasound images. A gradient is an image a gradient in an image is a change in intensity or color along with the direction. The magnitude of a gradient includes only the amount of change without a direction. The bottom row of this table appeared to fit the distribution of Benford's law as expected. Bottom row was the frequencies of leading digits of the magnitudes of gradients from an ultrasound image. Do the frequencies of leading digits in the bottom row appear to fit the distribution of Benford's law as expected? Or does it appear that the image has been corrupted with a substantial amount of noise because the leading digits do not fit the distribution of Benford's law? Right, we have a graph down over here which is pretty close. And we have a table up here. So for this, we do have the simple random sample. We of course have frequencies in this table. And if we were to try to calculate all the expected values, we could see that all of them are at least 5. The lowest one is 12. That's about 12. So those are all good. The null hypothesis for this is we would list out all of these percentages. So P1 would be equal to 0.301. Okay. The second proportion, so P2, would be equal to 0.176. P, not B, P3 would be equal to 0.125, and so on and so forth with all these listed out, up to P sub 9 that equal to 0.046. The alternative is that at least one of these is not equal. Again, which one is that? But that's not the point of the test. The whole point is to determine if all these percentages are actually correct. If we looked to do this test, we get a chi-squared value of 11.2792 and a p-value of 0.186, which is kind of high, right? That is that the conclusion that we can make from this is that there is not sufficient evidence to warrant rejection of the claim that the 271 leading digits fit the distribution of Benford's law. Let me know if you have any questions or concerns. Thank you.